Good weekend? 3 days is nice. After 4 days of pretty intense stuff, isn't it? And next weekend we get 4 days because we get 4th of July off. But that means we cram everything else up. So I'm not sure if we there you go. I'm not sure if we gain anything in the process of that. But what I'm going to do are a couple things. One is let you know how far the material will cover for the exam. It's almost certainly going to cover through what I finished today. Okay, so that tomorrow's material will be on the second exam, and I'll let you know at the end of the period about that. Second, I always try to do a review session for students, and in the summer they do get very scrunched up. So the review session will be tomorrow night after class. So I know you're tired, and I'm tired. Believe me, I'm tired as well. But right at 5 o'clock, we'll start the review session after class. If you can't hang around for the review session, you don't have to be here or anything. I will videotape it. So that if you can't be here, we can hopefully get it posted as quickly as possible and get it up there. Okay. Now, a couple people have questioned, are we're going to cover new material on the on Wednesday, because that's what it says on the schedule, and that's a sort of a tentative thing. It kind of depends on how far I get tomorrow, because we obviously only have a limited number of days to get through here. If I get far enough tomorrow through material, then we will have very little or none on the exam day, and we'll devote the period to taking the exam. Okay. One of the things about the summer term class is I give you more time to take the exams. Everything else is pretty scrunched up, so one of the advantages of taking the summer term class is you get a little bit more time. If you take it in the fall or something like that, then you've got you've got 50 minutes to get things crunched in. I'm not going to let you sit here for 4 hours, but I will also not rush you out at 50 minutes either. Okay? We all clear? Okay, so let's dive into our next topic, which is enzymes. And enzymes, of course, are really what I consider to be the magic of biochemistry. There's a couple things that are almost magical, and enzymes are one of them. Well, of course, magic doesn't exist, so I should use that word to describe them a little sparingly. But in essence, enzymes are magical because they work at rates that are pretty hard for us to conceptualize. It's very difficult for us to, I think, grasp what enzymes are really doing. And I hope in some of the things that I will show you today to convince you of just that. Okay? So enzymes are pretty interesting molecules. Without enzymes, we don't have the ability to catalyze reactions rapidly. And as we will see, again, you've already seen with hemoglobin, of course, how hemoglobin, as I said, was essential for animals to exist. Animals have very rapidly changing energy needs, and enzymes help organisms to meet those needs. Now, enzymes are important not just for animals, but they're important for every living system, because some of the reactions that we talk about have extraordinarily slow rates when there's no enzyme. Okay? And I'll give you some examples of that as I go through and talk about things. But some of these are extraordinarily slow. Some of them are extraordinarily fast with enzymes. And so the difference between the two is really remarkable. One of the enzymes I'm going to start to talk about is that of carbonic anhydrase. And carbonic anhydrase catalyzes a reaction that you actually saw something about when I talked about hemoglobin. You're going to hear more about carbonic anhydrase over the next few days. Carbonic anhydrase catalyzes the solubilization of carbon dioxide. And that solubilization happens in aqueous solutions. Carbon dioxide plus water gives us carbonic acid. That's H2CO3. Okay? And you can see that reaction going there. This enzyme that does this is absolutely remarkable at how efficient it does this reaction. Okay? It's absolutely remarkable at how efficient it runs this reaction. I'll show you some numbers for that in just a minute. But suffice it to say, this is the very simple reaction that's catalyzed by carbonic anhydrase. Okay? Okay. Another type of reaction that we might be concerned about in the cell, you've already seen how, I've already described for you at least how a protease worked. I told you that a protease broke peptide bonds. We saw examples of this with trypsin and chymotrypsin and carboxypeptidase and so forth. And in each case, the enzyme was breaking a peptide bond. We can see, in this case, a schematic representation of the breaking of that peptide bond right here. And the breaking of the peptide bond involves what we call a hydrolysis. Whenever we have water added to a molecule to break a bond, that is known as a hydrolysis. And we can see the hydrolysis reaction here. We had a peptide bond to begin with between the red carbonyl group and the blue amine group. When we add water across that, excuse me, we add water across that double bond, we see that we generate a carboxyl and we generate a free amine. In the process, we split the bond between the two pieces and end up now with a peptide that's been split in half in this case. Okay. Enzymes, as I said, are pretty magical. Now, this starts to give us some numbers, and I'm going to come back to these numbers later, but I just want to throw this out at you so that you get a feel for what an enzyme is doing. Okay? Now, the top reaction there is catalyzed by an enzyme, OMP decarboxylase. It actually catalyzes a very important reaction in nucleotide metabolism. You'll hear about nucleotide metabolism next term. And nucleotide metabolism relies on this enzyme. Well, you can see why it relies on this enzyme, because the half-life, that is the time it would take half of the substrate to be converted into product, for this reaction is 78 million years. It's not a reaction that goes very fast on its own. Okay? When we take and we treat the same substrates with the enzyme that catalyzes this reaction, we see that we go from something that takes 78 million years for half of it to work to a reaction where we're actually converting 39 molecules of substrate into product every second. Each molecule of enzyme is doing that. Okay? Now, if we do the numbers and we see the level of enhancement, the level of enhancement here is 1.4 times 10 to the 17th. Okay? Now, to give you an idea, all right, 10 to the 12th is a trillion. All right? 10 to the 15th is a quadrillion. This enzyme is speeding up this reaction by a factor of 140 quadrillion. Now, I don't know about you, but I don't use quadrillions very often in my descriptions of things. All right? The rate enhancement of this enzyme is nothing short of phenomenal. Okay? Well, not all enzymes catalyze reactions that start out that slow, but you can see that some of these are still pretty slow. Imagine I'm wanting to make a nucleotide and I'm waiting this long for my reaction to occur. Okay? It's a long time to have to wait. Enzymes help me to make these reactions occur much more rapidly. If we start with a carbonic anhydrase, we see that the reaction that it catalyzes doesn't take that long. Okay? And so its half-life is about 5 seconds, so it doesn't take very long without an enzyme. But we still see a pretty good enhancement of the rate. We see a rate enhancement of 7.7 million-fold. Okay? So that's still pretty darn good. All right? Nothing shabby about that at all. But the remarkable thing is right here. Okay? Now I'm going to come back and talk about this number in just a second. But this number is pretty phenomenal. What we see in this column is the number of molecules of product being made per molecule of enzyme per second. Now, carbonic anhydrase is catalyzing a reaction where it's making 1 million molecules of product per second per enzyme. Every enzyme is doing that. Imagine that you had General Motors cranking out 1 million cars a second. Okay? We can't conceptualize of those kinds of numbers in the macroscopic world. There's nothing I can do at the rate of 1 million times a second in the macroscopic world. My world doesn't work that way. But part of what this tells us is that something that happens at the nanoscopic level in solution is very different than things that we have a handle for in the macroscopic world. Okay? That's one thing that it tells us. The other thing that it tells us is that enzymes are doing something really interesting. Okay? Now I'm going to come to that interesting part in just a little bit, but I just give you this to give you a feel for what we're talking about in terms of what an enzyme is capable of doing. Okay. Enzymes are specific. Okay? They have varying specificities. All right? When I say specificity, I'm talking about the specificness of the molecule that it catalyzes a reaction on. We saw, for example, when I told you about trypsin, trypsin was able to cleave two substrates. It could cleave if this was a lysine or this was an arginine. Okay? That meant there was a little bit of flexibility in what it was able to catalyze a reaction on. There was a little bit of flexibility in there. And that flexibility arises partly from the flexibility of the enzyme and the chemistry of the active site. Those two things together affect whether an enzyme will work on a particular substrate or not. The bigger factor of the two by far is the shape of the active site. If the molecule doesn't fit in the active site, there's no way the enzyme can catalyze a reaction on it. Now, I'm using a term I haven't defined, so I should define that for you, and that's the active site. The active site of an enzyme is the place where the reaction is catalyzed. The molecules that the enzyme catalyzes the reaction on are called substrates. Some reactions may have one substrate, some reactions may have two, some may have three. But the substrate is the molecule that the enzyme is catalyzing a reaction on. Not surprisingly, the substrate is binding at or near the active site. So depending upon the configuration of that active site, some substrates may not fit. If they don't fit, enzyme just going to blow them off. It's not going to do anything with them. Okay. And let's see. Let's come back to that. I'll talk about that later. All right. Well, let's consider now the enzymes from an energetic point of view. And this is a place where students frequently make mistakes about how enzymes work because they didn't get a good grounding in their early chemistry. Okay? When I talk about energy, energy has a certain meaning for us. And what that meaning of energy is for you is probably different from what that meaning of energy is for me and for somebody else. Okay? So we want to make sure that we're all on the same page with respect to energy. When we talk about energy with respect to chemical reactions, we are interested in using information about that energy to predict the direction of a reaction. I mentioned this in the very first day of class, and we are concerned about metabolic pathways. Are they going forwards or are they going backwards? And the answer to that question ultimately lies in the energy of the reaction. Okay? The energy of a reaction will vary with the concentration of reactants and products. The energy of a reaction will vary with the concentration of reactants and products. It's a very important point. There's many different types of energy. There's enthalpy, okay? There's entropic energy. We're concerned with a specific type of energy known as the Gibbs free energy. Okay? The Gibbs free energy is very useful because the change in the Gibbs free energy for a reaction, known as the delta G, tells us the direction of a reaction. If the change in Gibbs free energy for a reaction is negative, the reaction goes forwards. If the change in Gibbs free energy for a reaction is positive, the reaction goes backwards. And if the change in the Gibbs free energy for a reaction is zero, the reaction is at equilibrium. Now, I'll talk later in the class about delta G. We're not going to do delta G calculations on this exam, so I can tell you that up front. I'm just introducing delta G because we have to understand that to understand enzymes. Delta G calculations will be on the second exam. Now, nonetheless, you need to know some things about free energy in order to understand enzymes. All right? The delta G for a reaction, as I say, determines the direction of a reaction. One of the misconceptions students have about enzymes is that they think that the enzymes change the energy of the overall reaction. That's absolutely wrong. Enzymes do not, underline, do not alter the overall energy of a reaction. Okay? So we have to start thinking, well, if enzymes don't alter the energy, and the energy is, in fact, a consideration for a reaction, then we have to start wondering, how in the hell are enzymes doing what they're doing? Okay? And that answer is going to come when we look at the mechanisms that enzymes use to catalyze reactions. Before I do that, I'll remind you about free energy. Again, these things we'll talk about for the second exam, but the Gibbs free energy, the change in Gibbs free energy for a reaction, delta G, is equal to a standard Gibbs free energy known as the delta G0 prime in biological reactions. In other reactions, it's called the delta G0. The delta G0 prime plus RT times the natural log of products over reactants. And it's because of this products-reactants ratio that the energy, the delta G, varies as the concentration of things change. If I increase the products, I'm going to increase the delta G. If I increase the reactants, I'm going to decrease the delta G. And again, we'll talk about that as we talk about things, we talk about metabolic energy later in the term. Okay? Now, what I want to do is spend some time now thinking about, well, how is it that enzymes can in fact speed a reaction without changing the overall energy? All right? In order to understand that, we need to think about what's involved in a reaction. Okay? That's not the one I wanted. Pulled the wrong one. What's happening in a reaction? Well, it turns out that enzymes do alter an energy component of a reaction. But it's a transient change. It's not an overall change. Okay? That's shown most clearly, I think, in this figure right here. When we look at this figure, we see a schematic representation of a reaction. So this is labeled on the x-axis as reaction progress, whatever that means. On the left, the reaction is before it starts, and over here is the reaction when it's done. Now, one of the things that I hope you remember from freshman chemistry and also from organic chemistry is that reactions have an energy barrier they have to get over in order for the reaction to start. That energy barrier is known as the transition state energy. Some people call it the activation energy, and I will accept either term. Either one of those is acceptable. This activation energy is the barrier to the reaction. Now, in this schematic representation, you can see substrate on the left, and you can see product on the right. And you notice that the free energy for the reaction went from this state down to this state. That decrease in free energy meant that the delta G was negative, meant that the reaction was favorable, and the reaction went forwards. Okay? Now, what we see is true for both an enzymatic reaction and a non-enzymatic reaction. The non-enzymatic reaction is shown in the solid line going above. We see that it starts at the same point as a catalyzed reaction, and it ends at the same point as a catalyzed reaction. That tells us that the overall energy of this reaction is not different for a catalyzed versus an uncatalyzed. So the enzyme is not changing the overall energy of this reaction. The delta G for this reaction is exactly the same for a catalyzed reaction as it is for an uncatalyzed reaction. Well, then what's all this business in the middle? Okay? Well, this business in the middle tells us that the enzyme allows us to cheat. It allows us to get the reaction going without having to go over that energy barrier. Now, the analogy, I like to make an analogy for this, and the analogy I like to make for this is that of a giant steel ball bearing. So if you've heard this analogy before, I apologize, but it's the only one I've got. It's the best one I've got. Imagine that we have a giant steel ball bearing. And we decide as a class we're going to take this giant steel ball bearing and we are going to push it into the ocean from Corvallis. Corvallis is about 250 feet above sea level. So in theory, we should be able to push it in the direction of the ocean. And since sea level is lower than Corvallis is, the ball bearing should get there. Well, you realize, of course, that's not going to happen because between Corvallis and the ocean, there are there is the coastal mountain range. Okay? So you say, oh, wow, we've got to think about that. There's my activation energy. I've got to get over the coastal mountain range. So let's, as a class, we'll take this giant steel ball bearing, so it's going to take all of us pushing it, and we want to make sure it gets over to the coast. So let's go and push the thing to Mary's Peak, because that's the highest point in the coastal mountain range. And if I get it to that highest peak in the coastal mountain range, I know it's going to have enough energy to get over all the other hills as it gets on its way over there. All right? So as a class, we all get out there, we all push this ball bearing up to Mary's Peak, and of course we assume that there's been clear-cut forests between Mary's Peak and the ocean, which in Oregon is a fairly safe bet, actually. Okay, so we've got a path for it to go. All right? We get to Mary's Peak and we push it off, and it's got enough energy, and it goes through those clear-cut areas, and sure enough, it goes and it eventually ends up at the ocean. Okay? Now, any engineers in here? Yeah. Engineer says, well, that's a stupid thing to do. You push it to Mary's Peak, you push it to the very highest point, okay? There's got to be a more efficient way to get this out of there, and there is. Why should I push it to Mary's Peak? All I have to do is make sure I get it over the passes, and I've got it there. So what the enzyme is allowing you to do is to find the smaller energy to get that ball over to the peak. It's taking you over the passes instead of taking you over the highest mountain. The uncatalyzed reaction takes you over Mary's Peak. The catalyzed reaction takes you over the passes on the way to the coast. Okay? It takes a lot less energy if we go over the passes. We'll get a lot more ball bearings over in the ocean, okay, if we take that route than if we take the other route, because it's going to take us more time and it's going to take us a lot more pushing to get us up to the top of Mary's Peak. Because we're more efficient, because it is easier to reach this point right here, molecules have sufficient energy, many more molecules have sufficient energy to reach that activation energy and make it there. Now, how is it that the enzyme is able to do this? How is it that the enzyme can do this? A chemical catalyst can do this as well, but enzymes turn out to be millions of times more efficient than chemical catalysts. I said that right. They are millions of times more efficient than chemical catalysts. The reason that they're millions of times more efficient than chemical catalysts is that enzymes are flexible. Again, we come back to that notion. We will see, I think it's either tomorrow or Thursday, how that the flexibility of an enzyme leads to this property. But enzymes have flexibility. Chemical catalysts don't have flexibility. And that flexibility gives some enormous advantage to enzymes. Let's think at the enzyme level. How is it that this enzyme is actually making this process happen so effectively, so efficiently? Okay? Imagine I have two molecules, molecule A and molecule B, and they react together to make a new molecule C. They combine. Okay? Let's think about that. Let's think about how that might happen. If I have the uncatalyzed reaction, I have molecule A over here in the gaseous state. This could be in solution or gas. It doesn't really matter. Okay? I've got molecule A over here, and I've got molecule B over here. And what's got to happen in order for them to react? Well, first of all, they've got to bump into each other, right? The likelihood they're going to bump into each other is a function of their concentration. So we see concentration coming into play. But when we look at a chemical reaction, one of the things we don't really think about, but we need to think about, is what's the geometry with which they're hitting each other. Okay? Let's imagine I've got an amino acid as one of the molecules. That amino acid has a carboxyl end and it has an amino end. If the amino end bumps into the enzyme, it reacts. If the carboxyl end bumps into the enzyme, it doesn't react. Not the enzyme, but I'm sorry. If A is an amino acid, the amino end bumps into B, it reacts, but the carboxyl end bumps into B, it doesn't react. So we realize that the geometry of that collision that happens between two molecules has to be right. There's going to be a lot of bumping into each other in a non-enzymatic reaction that aren't going to result in anything. They're going to be non-productive. The enzyme overcomes that, because what the enzyme does is it has a specific binding site for A. It has a specific binding site for B. All right? So you can begin to see now that the binding sites of the two enzymes that are here, the binding sites are already putting A and B into the proper geometry. They've been put into the proper geometry. If I had to wait for this to happen of A bumping into B, sometimes they bump into each other in the right way. Other times they bump into each other like this. Nothing happens. The enzyme makes the interactions be productive. The geometry is right in order for that reaction to occur. Okay? That's one component. The second component is because of the flexibility of the enzyme, not only does A bind over here and B bind over here, but the binding of A and B cause that enzyme to change shape ever so slightly, and when they do, the electronic configuration of putting these together is idealized. Okay? So we've got them bound here, the enzyme changes shape, bang, now we've got a very favorable electronic configuration. That electronic configuration favors the reaction that I'm interested in catalyzing. So the enzyme is very, very effective at not only arranging the molecules as they need to be arranged, but actually putting the electron clouds together in the way that they need to be put together. Now, enzymes catalyze things besides A plus B going to C. They can also catalyze the reverse reaction, C going to B plus A. Imagine the enzyme binds C, okay, and the enzyme changes configuration once it's bound C. It's going to change configuration in the backwards direction, and now it's going to put strain on these. What do you suppose is going to happen to B and C? Well, the strain is going to pull the bond apart. Enzymes catalyze forwards and reverse reactions. That's very important. They don't cause it to go only one way. They cause both reactions to get sped up. The forward reaction is sped up zillions of times. The backwards reaction is sped up zillions of times. As a consequence, enzymes, and if here's one message to take away, here it is, enzymes speed the achievement of equilibrium. They speed how fast an equilibrium is reached. Because at equilibrium, the forwards reaction and the backwards reaction are occurring at equal rates. The enzymes speed that up tremendously. If I leave a system alone to itself, it will reach equilibrium on its own, but that might take 78 million years. The enzyme allows that equilibrium to be reached much, much faster. It doesn't change the equilibrium because that would involve changing the overall delta G. It does not change the equilibrium in any way, shape, or form. It simply speeds how fast that equilibrium is reached. Okay, now I'm doing a lot of talking. I'll stop for questions. Questions about that? Hearing none. Well, you guys smell that stuff in the air. Isn't that awesome? What is that? What is that scent? I noticed it coming in the building. Anybody know what that is?
It smells like cut grass.
No, I smell it. Very sweet smell. People notice it? It's what?
It smells like dandelions.
Dandelion? No, it's not dandelion. It's odd because I usually have a terrible sense of smell, but yeah. Do you know what they are? Boy, it's sure awfully strong. Okay. My wife and I always have this thing. She can smell, she can smell literally somebody who walked down the hall with perfume like an hour before. And she says, "Do you smell that?" I go, "No, I can never smell it." So when I smell something and somebody else doesn't, you guys must be dead. I don't know. Maybe the lecture is getting to you here, huh? Hopefully not. Okay, so this makes sense? Clear what enzymes are doing, not so much what, but how they're doing it. Okay? So they're not changing the overall equilibrium. One point I want to make here, and it was also listed on one of the slides earlier, and I'll make it here verbally, and that is that one of the big problems students get out of general chemistry is they never really got taught what equilibrium means. Okay? Half of you, when we talk about delta G problems later, half of you are going to try to tell me that equilibrium means equal concentrations of substrates and products, and it's not. Okay. Equilibrium does not mean equal concentrations of reactants and products. It means that the rate of making reactant is the same as the rate as making product. That's what equilibrium means. That might mean I have 10 times as much reactant as I have product. It might mean I have 10 times as much product as reactant. Depends on the reaction, obviously. But once I reach that, it will not change. That's what equilibrium means. We'll talk about that later. Okay. All right. Now, enzymes, one of the things that we're interested in studying enzymes is we are interested in understanding rates of reactions. That was the first thing I told you about enzyme, was they sped the rate of a reaction up enormously. One of the ways that we characterize enzymes is by how fast they do that. Okay? So we want to understand how fast it is that enzymes work. So we need to study a discipline. No, sorry about that. I keep walking over here. I'm a stroller, so you don't need to move your feet if you don't need to. If I trip, I trip. So that'll be my risk. Okay? Then I'll sue you. But okay. We're interested in what's called kinetics. Okay? Kinetics meaning motion. And for an enzymatic reaction, motion is basically the reaction that's being catalyzed. We're interested in understanding, okay, how fast a reaction goes. Okay? Now, what you see on the plot is something that's known as a plot of velocity versus substrate concentration. More commonly, we call it a V versus S plot. And it's here that I remind you that whenever you write a plot, you always label the axes or your plot is automatically wrong. It's important to label the plot because without that, a curve has no meaning. Okay? This plot shows us something about enzymatic reactions. It's not totally surprising. It's not as surprising as the other things I told you, I think. It says the following. If I start a reaction, well, let's think about how this plot was made. How do I do a plot of enzyme kinetics? First of all, in order to plot it, I need to understand what I mean by velocity. When I say velocity of a car, I'm thinking of how many miles per hour it moves down the road. Okay? When I think of a velocity of a reaction, of course, there's no distance being traveled. So miles per hour doesn't make any sense. Centimeters per second doesn't make any sense. Instead, with a reaction, I'm thinking of how fast it is I'm turning substrate into product. So the velocity that I am interested in is the rate of formation of product. And I measure that by the concentration of product divided by time. Concentration of product divided by time. Okay? Now, that's number one. So what's plotted on the y-axis is the concentration of product divided by time. On the x-axis, I have various substrate concentrations. Now, if you've never done an enzymatic assay, or even if you have, I want you to understand how it is that a kinetics experiment is done. So in order to do a determination of, to make a plot like this, here's what a scientist would do. First of all, they would have their enzyme purified. Okay? So they went through some of the purification methods that we talked about last time, and they've got their enzyme purified. Okay? So they've got pure enzyme sitting here in this tube. They're interested in how fast it's catalyzing a reaction, so they know that one of the variables turns out to be how much substrate that the enzyme has to work on. Let's imagine for a moment that I have an enzyme and I put it into a tube and I have, let's say, 1,000 molecules of enzyme. And let's say that I have 1,000 molecules of each of the substrates. It's a very dilute solution. The enzyme, if it were to get a hold of those substrates, would convert those substrates into products very quickly. Right? And notice I said if it got a hold of those substrates. What's got to happen when I have very, very low amounts of substrate? Well, it turns out that the limiting factor is how fast the substrate can diffuse to the enzyme so the enzyme can catalyze it. At low substrate concentrations, the rate is going to be slow because the enzyme is sitting here twiddling its thumbs, waiting on substrate. As I start increasing the substrate concentration, it gets more and more likely the enzyme is going to encounter substrate, and I measure a velocity that goes up because the enzyme isn't spending as much time twiddling its thumbs. Okay? Let's imagine that I am the president of General Motors, and I am, in fact, in the business of making automobiles, and I've got a factory full of workers. Ready? And they're all ready to make automobiles, and I give them only enough raw materials to make 1 or 2 automobiles a day. Okay? That factory is not going to be very efficient because I've got all these workers waiting for raw materials so that they can, in fact, put those together to make an automobile, but you're only giving me enough raw materials to do 1 or 2 a day. Got a problem. So I'm the president of General Motors, and I said, okay, this factory over here is not very efficient, but good God, we forgot to give them materials. We've got to make them efficient, so let's give them 10 times the amount of material we were giving them before. Okay? Well, the factory says, oh, so they start turning out 10 times as many cars as they did before. As I increase the concentration of the materials, I start making more product. Now, imagine that I'm the president of General Motors, and I'm a rather stupid person. And so I look at this, not to cast anything on General Motors, okay? Not to say that any of the leaders of our various industries would not have some of the brains that they need to, but let's say that, suppose theoretically, that this president of General Motors is not very smart and says, oh, well, we added 10 times as much and they put 10 times as many cars, so let's give them 1,000,000 times as much raw materials. We should be making so many cars that we will fuel the world's automobile needs, right? Well, they deliver 1,000,000 times as much if they were even capable of doing that to this factory, and the factory's production goes up by a factor of maybe another 10, but then it levels off. Why does it level off?
It's already saturated?
It's saturated. They have gotten all the materials. They're at capacity. There's only a limited capacity that that factory has. Now, what this curve is showing you, first of all, is that enzymes have the same property. Okay? They have a limited capacity. When we start increasing materials from very minuscule amounts up to greater amounts, we see that velocity go up, but then we start seeing it flatten out. Flattens out. Yes?
Will the maximum velocity increase if you add more enzymes?
Very good question. You're actually getting ahead of me, but the answer is yes, it will. If I double the number of factories for General Motors, I will double the number of cars that's at maximum capacity, and so too will I double the concentration of product for an enzyme. And what you said is very important. Vmax is not a constant for an enzyme. People think it is. It's not. It depends on the amount of enzyme that I used. Now, I started telling you how I was going to do this experiment. I got distracted, so I'm going to come back and tell you how we do the experiment. But your point's a very good one. Okay, everybody got that? Vmax is not a constant. It depends on how much enzyme we use. I double the amount of enzyme. Just like I double the factories, I'm going to double the number of cars. So too will I double the amount of product. Okay, now, how to do this experiment? Well, I've got all these things in my head, so I'm thinking, oh, wow. So the enzyme velocity is going to vary as I change substrate concentrations. So let's do a series of about 20 reactions. We'll take 20 little tubes, and into those tubes, I'm going to put some substrate. I'm going to put some buffer. Okay, and then I'm going to put some enzyme. But I have to be careful because in each one of these tubes, I want to put the same amount of enzyme because I don't want to have the enzyme be a variable. What do I want to be the variable? Substrate. So the 20 different tubes will have 20 different concentrations of substrate. The same amount of enzyme, and there's one other thing I've got to keep the same. What is it? What's that?
The buffer?
Well, the buffer is the same. Okay, this buffer is the same, but I have to keep one other variable the same in this experiment.
Temperature?
Temperature's another one. Good. That's not the one I'm looking for, but you guys are getting them. These are all considerations. Time. Okay? Time is a factor. Now, time turns out to be an interesting factor. Okay? Why is it an interesting factor? Well, what did I say about what an enzyme does? I said it sped reaction, but I said it sped both the forward and the reverse reaction. The forward reaction sped up, but so is the reverse reaction. Well, if I'm interested in studying the forward reaction, what's going to happen over time? The reverse reaction is going to start happening, right? So we use a trick. We use a trick when we're doing enzyme kinetics. We measure the velocity for a fairly short period of time before the reverse reaction gets much of a chance to go backwards. So when we start, we're measuring only the forwards, and if we don't measure it for too long, we're essentially not going to get any backwards going with that. So we measure, and when you look in other textbooks, you'll see something called V0, and that's basically what the velocity is. It's the velocity that is the very early velocity that happens in that tube. Okay, so now I've got my parameters all set up. I've got a short time frame, maybe a couple of minutes. I've got my fixed amount of enzyme. I've got my fixed buffer. I've got my fixed temperature. I let my reaction go, and I measure the concentration of product that I get. And then I plot. For each of the individual tubes, I plot what was the substrate concentration, what was the velocity I got. What was the substrate concentration, what was the velocity. That's how I got this graph. And if I do this, what I see is just what you see on the screen. It will level off at a point where I've reached capacity. And that capacity is known as maximum velocity. The maximum velocity of a reaction is when the enzyme is saturated with substrate. Just like when that factory is saturated with raw materials, it can't go any faster. It's limited only by the amount of work that the workers can do. This enzyme is saturated with substrate. It's not waiting for substrate. As soon as it lets go of a product, another one's there, because its concentration is high enough that the enzyme isn't spending any time waiting on substrate. Okay? Everybody got that? How am I doing on time? Okay. Now, we're going through some cool concepts here. Let's see. Blah, blah, we don't need that. Okay. Now, if maximum velocity is not a constant for an enzyme, it doesn't make any sense for me to be comparing Vmax. It's called Vmax. Maximum velocity is called Vmax. It doesn't make any sense for me to compare Vmaxes between two different enzymes because Vmax varies with enzyme concentration. And since enzymes have different molecular weights, there's all kinds of variables for me to consider. I want to know something that's characteristic of the enzyme and not of the concentration of the enzyme. So I need to have a different parameter when I'm comparing the rates of two different enzymes. The parameter that I need is something called the turnover number. It's also called Kcat, K with a subscript of CAT. Okay? How do I get Kcat? I'll tell you how I get it, then I'll tell you what it is, because you've already seen it, you just didn't realize it. Okay? Kcat is determined by taking the Vmax, so I've done my experiment, I've got my Vmax, and I divide Vmax by the concentration of the enzyme that I used in all of those tubes. So I had a concentration of substrate, a concentration of product, that was my velocity. I divided that concentration of product by the concentration of enzyme, so the two concentrations disappear. I've taken the concentration of the enzyme out of the equation, and I'm left with a number per time. Remember, I had concentration per time. That's what velocity was, right? I now have a number per time. So if I get Kcat for an enzyme, it's going to be something like 1,000 per second. And what that means is 1,000 molecules of product per molecule of enzyme per second. Okay? Oh, wrong one. And that comes from, why is this? that actually was what we saw right here. When we saw this number, there's your Kcat. So when I said carbonic anhydrase was producing 1 million molecules of product per molecule of enzyme per second, I can compare carbonic anhydrase to chorismate mutase, to triose phosphate isomerase, to all these other enzymes, and I can say, wow, this guy wins the speed race because it's got the highest number of molecules of product per second of enzyme. I can't compare Vmaxes of those, but I can compare, I can compare them, but they won't have any meaning. But I can compare Kcat and have meaning by the magnitude of the number. Kcat is a very, very useful parameter for me to understand in studying an enzyme. Okay. Everybody understand what Kcat is?
So
Yes, sir.
Is that the fastest they can catalyze the reaction, or is that just what does it a certain?
It's a common question. Is that the fastest it can catalyze a reaction? The answer is yes, because I determined Vmax, which I had established was the fastest it could catalyze a reaction because the enzyme was saturated with enzyme, with substrate. But yes, you're right, and that's a very common question, a very good question. Other questions? Okay, maybe that's a good stopping point to take a brief break, and then we'll come back and talk about, we've got a lot more parameters to talk about with enzymes, but that's a good place for us to stop and catch our breath. Your brain's all stretched yet?
So, what do you put Kcat as absolute velocity?
Would it be appropriate to do what? Say it again.